In this chapter, we're going to solve questions about plane figures using trigonometry. In example 1, we have an isosceles triangle with angle alpha 70 degrees, base b 4 centimeters, and we should find its area. Try to solve the task by yourself and then have a look at my solution, so stop the program now, and here comes the solution. The area of the triangle can be calculated as 1/2 times the side b times the altitude h. Let us now look at the triangle BHA, which is a right-angled triangle at h. We know the angle alpha, we know the length of this side here because HA is b/2, and what we're looking for is the altitude h. So with respect to the angle alpha, this side is the opposite, this side is the adjacent, so we need to use the tangent. And we get the tangent of alpha is h divided by b/2. We multiply now by b/2 and we switch sides, so we get h is b/2 times tangent of alpha. Let us now insert this into the formula for the area of the triangle. And we get the area of the triangle is 1/2 times b times the h, so times the b/2 times tangent alpha. This simplifies to 1/4 times b squared times tangent of alpha, and we insert the values now, and we get 1/4 times 4 squared times tangent of 70 degrees, which simplifies 4 times tangent of 70 degrees, and we get in the end that the area of the triangle is approximately 11 centimeters squared. In example 2, we're given a rhombus with side length 5 decimeters and an angle alpha of 30 degrees. The task is to find its area. In solution 1, we find the area based on the diagonals, so use the trigonometry to find the diagonals. Try it on your own and stop the film now. And here comes my result. Because the rhombus is a kite, ein Drachenviereck, we can calculate its area as 1/2 times e times f, the length of the diagonals. Also, because it's a kite, we know that the two diagonals are perpendicular to one another, and so this triangle here is a right-angled triangle. Since the rhombus is also a parallelogram, this length here is half of the diagonal and this as well. Now let us look at this right-angled triangle. We are given the length of the side A and we're given the angle alpha half here, and we're looking for this side E star. Well, E star is the adjacent of this angle and A is the hypotenuse in this triangle, so we need the cosine. So we find that cosine of alpha half of this angle here is E star divided by A, and solving for E star we have to multiply by A, and we find E star is A times cosine of alpha half. We want to find also f star. Well, with respect to alpha half, f star is the opposite, A is still the hypotenuse, so we know the sign. We get that sine of alpha half is f star divided by A, and so solving it for f star, we get f star is A times sine of alpha half. Now inserting this into the formula for the area, 1/2 times E times F, we get 1/2 times 2 E stars times 2 F stars, since E is 2 E star and F is 2 F star. This simplifies to 2 times E star times F star, and now inserting these results we get this here, and this simplifies to. So inserting the values we get 2 times 5 squared times sine of 15 degrees times cosine of 15 degrees, and so we find an area of approximately 12.5 square decimeters. Now try to find the area in a second way using the altitude HA, again using trigonometry. Do it on your own, stop the film, and here comes the solution. The area of a parallelogram is a side times the corresponding altitude, so A times HA. Let us look at this right-angled triangle here. The angle alpha is given, The hypotenuse D is also given since it's the same length as A, so just 5 decimeters given. And what we're looking for is the opposite HA, so we need to use the sine. So sine alpha is HA divided by D. D is equal to A, so sine of alpha is HA divided by A. We multiply with A and change sides, and we get HA is A times sine alpha, and now insert that into the area formula. So we get A times sine alpha. So A squared times sine alpha. And inserting the values, we get 5 squared times sine of 30 degrees, which is 25 times, and this is, as we learned just in the last chapter, 1/2, so it's exactly 12.5 square decimeters. Have a look at example 3 and try to solve it by yourself, and stop the film. And here comes the solution. To find the length of the perimeter, we need to find the length of one such side of such a triangle. Well, there are in total 12 such triangles. We'll look just at this right-angled triangle. We know the length of the hypotenuse, it's the radius of the circle. We can find this angle here, and what we're looking for is this length x, which is the opposite of this angle. R is the hypotenuse, so we will need the sine once we know this angle. The angle is just half of this full angle, and there are 12 such triangles in total for the full circle, so this means it's a 12th of the 360 degrees. Let us call the angle theta. Theta is 1/2 of 1/12 of the 360 degrees and is hence 15 degrees. We said we need the sine of the theta, so sine of theta is x divided by r. Multiplying by r and changing side, we get x is r times sine of theta. Now that we know x, we know that this length of the triangle side is 2x. There are 12 such triangles, so the perimeter is 12 times 2x. So we get 24 times r times sine of theta. Inserting the values, we get 24 times 13 times sine of 15 degrees, and this is approximately 80.8 millimeters.